Hello everyone, today we'll talk about the solution to the problem Bitwise XOR of all pairings. There will not be much coding here because this is more of a riddle, and it's a riddle that of course assumes that you know something about Bitwise XOR. So if it's completely new to you, then feel free to read up on it. It really just means that you take two numbers, you look at their binary representation, and when on every position the result will have a 1 if exactly one of the two numbers has a 1. So one number has to have a 1 at that position, the other has to have a 0. Another way of looking at Bitwise XOR is that you take one number and the second number has zeros and ones on different positions, and it tells us, whenever we have a 1 on a given position, that we should flip that bit in the original number. And if we have a 0, we should leave that bit unchanged. And this is important to understand one interesting property of XOR, because XOR, like addition and multiplication, since it's of course just addition modulo 2 on every separate bit, it is associative, it is commutative. Essentially you can rearrange the elements that you are XORing together however you like and it doesn't change the result. But for addition, if you want to go back, you have to subtract. For multiplication, if you want to go back, you have to divide. Well, not really, you can multiply by an inverse or something, but there is this addition, subtraction, multiplication, division. So what is the inverse operator for XOR? Well, it is XOR again. And this interpretation of flipping bits is easy to show why that works, because you take a number and you take another number which specifies which bits to flip. If you do it twice, then you flip some bits and leave some bits unchanged, and then you flip those bits again and leave those other bits unchanged. So every bit in the original number was either left unchanged or flipped twice. Flipping twice is as if you left it unchanged. So the whole number is left unchanged. And this is the crucial observation to solve this problem, and to solve probably the vast majority of XOR problems, that XOR is its own inverse. Because now, when you want the XOR of this hypothetical array nums3, we should first of all consider commutativity, and notice that we can look, for instance, for every occurrence of every number together. And now, since we know that for XOR, if a number appears twice, we can cross out both of those appearances. We only care about if a number appears an even number of times or an odd number of times. And for every number from nums1, it appears in a pair with every number from nums2, which means that if there is an even number of numbers in nums2, then that number from nums1 will appear an even number of times. If length of nums2 is odd, it will appear an odd number of times, and so it doesn't cancel out and it gets into the result once. So the result starts at 0, and now for every number in nums2, we add it to the result, we XOR it with the result, only if there is an odd number of numbers in nums1. So if len nums1 and 1 is true. And of course we want to then add everything from nums2, so we just XOR it. So we reduce using XOR this array nums2 to a single value, and we XOR it into our result. And likewise for values from nums1. They only count if each of those values appears in an odd number of pairs. So if length of nums2 is odd, we reduce nums1 with XOR, XOR it into the result, and at the end we return the final result.